Collecting data on cyclones is obviously very challenging despite all the new technology like drones, little aircrafts flying through them, rockets falling through cyclones, and so on. We still don't have a very good sense of a consistent changes that have occurred or are expected to occur with global warming, ocean warming. Generally, it's now agreed that theory and numerical models indicate that tropical cyclones will strengthen with rising ocean temperatures. So recent paper from the GFDL group Murakami showed that the total number of tropical cyclones has actually decreased globally and in each basin. I think you can check, but it's expected that the number of the strongest of the cyclones will increase with further warming. There has been slowdown of cyclones, more rainfall associated with them, rapid intensification, all those things we have discussed. This nice paper that just came out in Nature, Shengping Shi's group argues using ocean current data, which are measuring, which have managed to get stuck in a cyclone for long enough to provide some data about how the ocean currents and the ocean mixing has changed under tropical cyclones over this period of 1991 to 2020. So it indicates that even though models have reached broad agreement on projected TC intensification, observed trends in TC intensity remain inconclusive and under active debate in all ocean basins except the North Atlantic, where aircraft reconnaissance data greatly reduce the uncertainty, so we can say something more robust about the hurricanes in the northern Atlantic. The conventional satellite-based estimates are not accurate enough to ascertain the trend in TC intensity, suffering from contamination by heavy rain, clouds, breaking waves, and spray. So even if you have a good satellite pass on a cyclone, you have all these issues with representativity or extraction of data under the cyclones to evaluate the trends. Here we show that weak TCs, that is tropical storms to category 1 TCs based on the Saffir-Simpson scale, have intensified in all ocean basins during the period 1991 to 2020 based on huge amounts of highly accurate ocean current data derived from surface drifters. So under stronger cyclones, stronger than category 2, the drogues may get submerged because of the strong mixing, or they might get blown away and so on. So you get reliable data for weak category 1 tropical cyclones. These drifters have submerged Holy Sock and drogues at 15-meter depth to reduce biases induced by processes at the air-sea interface. So they are hanging below the surface with this drogue so that they're actually following the currents and not being blown around by the winds and so on. And thereby accurately measure the near-surface currents even under the most destructive tropical cyclones. The ocean current speeds show a robust upward trend of 4 centimeters per second per decade globally, corresponding to a positive trend of 1.8 meters per second per decade in the tropical cyclone intensity. Our analysis further indicates that globally tropical cyclones have strengthened across the entirety of the intensity distribution. These results have a historical baseline that is crucial for assessing model physics, simulations, and projections, given the failure of the state-of-the-art climate models in fully replicating these trends. So you have the best analysis you can do of the observed tropical cyclone data, and then you look at what the models have done, and models of course have been inadequate in capturing some of these trends. So let's just look at some of the results briefly. This is a nice paper and not a very long paper, so you can go back and read it, and still I'm going to just highlight some points and not go into all the details. So here is the data distribution. Data points of drifters in pink dots that are located within a distance from the tropical cyclone center of r less than 7 r max, so the radius of the cyclone. This is under weak tropical cyclone conditions, and the number of corresponding weak TC centers in a 6 degree by 3 degree grid box. So the blue contours shown here for 50, 100, 200, 300, 500 and 700 cyclone centers. During the period of 1991 to 2020, the total number of drifter records is 85,411, and this is done using MATLAB. So the regions looked at are the Northeast and Northwest Pacific, the Atlantic, South Pacific and South Indian Ocean. The North Indian Ocean is not considered due to the lack of reliable data and conclusions to be drawn there. So these are the currents. So evolution of the near surface ocean current speeds under weak tropical cyclones going from 1991 to 2020. Sorry to be flipping back and forth. I split the figure because it's too long. So here is the North Atlantic showing a statistically significant upward trend with this slope and significance. This is the p-value, and this is for the Northeast Pacific, Northwest Pacific, South Indian Ocean, South Pacific Ocean and the global ocean. And here you have the best track data and the drifter data showing the corresponding probability PDI potential. Just a second. So this is all done with great detail in data analysis that I'm not going to go into here. So let's, oops, my PowerPoint is stuck. Just give me, sorry about that. For some reason the PowerPoint gets stuck once in a while. So we are also looking at the power dissipation index, which also shows an upward trend over this period, and further details include mean near surface ocean current fields under weak tropical cyclones. This is the global mean here, and you can see the period of 1991 to 2005 and 2006 to 2020 in centimeter per second and the difference. So obviously there has been a significant increase in the currents under the cyclones during this going from the first 2 decades to the latter 2 decades, or 2 decades or so. And this is also true for the North Atlantic, Northeast Pacific, Northwest Pacific, Southern Indian Ocean and the South Pacific. So clear trend in the strength of the currents under the cyclones, which are directly related to the winds of the cyclones. And the table shows the numbers. So statistics of drifter measured ocean current speeds under weak tropical cyclones for all of these basins that we mentioned for 1991 to 2005 and 2006 to 2020. Just looking at the change in terms of the maximum and the mean, you can also see the maximum and mean currents for each period. And there's been an increase in the maximum and mean of 8.2 and 4.1 respectively. And that's in the North Atlantic. For the Northeast Pacific, it's 11.4 versus 3.2 in the maximum and the mean. Northeast Pacific is the region where 30% of all tropical cyclones are born, which go on to become typhoons and hammer into the Asian countries there, ranging from Philippines into Taiwan, Korea, China, Japan, and so on. Northwest Pacific, 16.1 and 2.0 it changes in maximum mean current speeds under weak TCs. South Indian Ocean 7.4 and 4.4, South Pacific 21.8 and 9.0, and globally it's increase of 12.5 in the maximum currents and 5.0 centimeter per second in the mean currents. So significant. And of course cyclones always create a strong ocean mixing, which is shown here, estimated as sea surface cooling induced by weak tropical cyclones. This is sea surface temperature anomalies induced by weak TCs for the period of 1991 to 2005 and 2006 to 2020, and these are the differences. And you can see that there is increased cooling in the strongest part of the cyclone by about 0.15 degrees C over these decades, which are also statistically significant. So it's a brief introduction to a paper that shows how cyclones have gotten stronger, but using a very new approach of using ocean currents under cyclones to infer the strengthening over these decades. Okay.